Oxidation states. To identify the oxidation states of elements when they're alone, in a compound, or in their ionic form, you just need to memorize a few general rules. Each pure element has an oxidation state of 0. This applies to homopolyatomic molecules as well, so molecules consisting of more than one identical atom, such as H2 and O2. The charge of an ion is equal to its oxidation state. For example, Cl- has an oxidation state of -1. In the case of polyatomic ions, the sum of all the individual oxidation states must be equal to the total charge of the ion. The alkaline metals, group 1, all have an oxidation state of +1. The alkaline earth metals, group 2, all have an oxidation state of +2. Aluminum's oxidation state is always +3, no matter what compound it is found in. Usually, oxygen has an oxidation state of 2-. However, in any compound in which oxygen is in the form of peroxide, O2, 2-, like in H2O2, its oxidation state is -1 instead. Hydrogen usually has an oxidation state of +1. However, in compounds where hydrogen is in its anionic form, like NaH, its oxidation state is -1. Fluorine always has an oxidation state of -1. The oxidation state of other halogens is negative when in the form of a halide, Cl-, Br-, I-, but positive when attached to an oxygen atom. We need to remember that one element can have several different oxidation states, depending on which compound it is found in. To find the unknown oxidation state of an atom in a compound, we always start by identifying the oxidation states of the elements we know already. For example, it's easy to find the oxidation state of oxygen, hydrogen, and fluorine. The rules we talked about earlier allow us to find many other oxidation states as well. Next, we can figure out the oxidation states of the remaining atoms by finding the sum of the known oxidation states, because we know that this sum must be equal to 0 for neutral compounds, or to the charge of the molecule if in the presence of an ion. Let's look at H2SO4 and try to find the oxidation states of each element. Let's start with the oxidation states that we know. We know that oxygen will be -2 and that hydrogen will be +1. To find the oxidation state of sulfur in this compound, we need to take the sum of the oxidation states of the other atoms. Don't forget to multiply the numbers by the number of times we find the element in question within the compound. Since this molecule is neutral, the sum of all the oxidation states has to equal 0. We get 2 times +1 for hydrogen, plus sulfur's oxidation state that we're looking for, plus 4 times -2 for oxygen, all has to equal 0. This gives an oxidation state for sulfur of +6. We know that alkaline metals like sodium have an oxidation state of +1, and that the oxidation state of oxygen is -2. The sum of all the oxidation states must be 0, so by calculating 2 times +1 for sodium, plus the unknown oxidation state of carbon that we ignore for the moment, plus 3 times -2 for oxygen is all equal to 0. We find that the oxidation state of carbon is +4. Note that here we're in the presence of a polyatomic ion with a charge of -2. That means that the sum of the oxidation states has to equal -2. Doing this calculation, we find that phosphorus has an oxidation state of +5. The sum of all the oxidation states must equal 0. Be careful here, we might get confused because usually sodium has an oxidation state of +1 and oxygen has an oxidation state of -2, which would not give us a sum of 0. We have to remember our rule that oxygen changes its oxidation states in peroxides. We know for sure that sodium always has an oxidation state of +1 no matter what, so we have 2 times +1 for sodium. Then we can put oxygen as our unknown value, even though we already know that it will have an oxidation state of -1 for oxygen in a peroxide. Don't forget to divide by 2, since we have 2 oxygen atoms in our compound, both having the same oxidation state.